In this problem, we're going to find V0 using superposition. We'll use our problem-solving strategy entitled Applying Superposition. If you remember with superposition, we're going to take and analyze a circuit with just one source active. So, for instance, we'll find the response, or V0, with only the 8 milliamp source active. We'll set the other two sources, we'll turn them off. Remember, if we turn off a voltage source, this becomes 0 volts, which is a short. This becomes 0 amps, which is an open. So really we're going to find the value of V0, or the contribution to the output voltage from each source acting alone. And then we'll add all those together to find the response when all three sources are active. So let's start with the 8 milliamp source. So we're going to now turn this one to 0, and we're going to turn this one to 0. So the resulting circuit is here. So here now we're going to find the contribution of this source to the output voltage. So if we look, for instance, we have these two resistors in series. So let's take and redraw the circuit. Now V0 prime doesn't appear on this circuit. Now let's take and combine these two resistors in parallel. When we do that, these two in parallel become a 2K. This one becomes a 3K. Now, let's find I1 prime. And we can do that by current division. We have a current divider here. We have a current entering and split between these two resistors. So I1 prime then is 8 milliamps times 2K over 2K plus 3K. And that's 3.2 milliamps. Okay, back up in this circuit. This is I1 prime equal 3.2 milliamps. Also, back in our original circuit, this is I1 prime. So then V0 prime is 1K times 3.2 milliamps equal 3.2 volts. Now, our next step is to go in and analyze a circuit with one of the other sources active. So now with the 12 volt source active, here's our circuit. We turned off the two current sources. We replaced them with open circuits then. So now here's our circuit. And again, let's begin to analyze. Let's take those two and put them in series again. Okay, there's the circuit that we have. Now let's combine those two in parallel. So our circuit then reduces to the following. Now, let's define this voltage as V1 double prime. We can calculate that from voltage division. So V1 double prime is 12 times 2K over 2K plus 3K, which is 4.8 volts. In this circuit, this is the voltage V1 double prime. This is also the voltage V1 double prime. Now, if we look, we have a voltage divider here. So V0 can be found, V0 double prime can be found by voltage division. We have 4.8. We want the voltage here. We have 1K or 1K plus 2K. And that tells us that V0 double prime then is 1.6 volts. That leaves us one additional source to look at its contribution, and that's the last current source, a 2 milliamp source. There's the circuit. Again, we need to analyze this circuit. So if we look now, for instance, these two resistors are in parallel. If we combine those, here's what our circuit becomes. So these two combine here. We have 2 kiloohms here, 2 milliamps here, 1 kiloohm here. Here's the voltage V0 triple prime. Now again, we have a current divider at this node. I'm going to define this current as I1 triple prime, and that's equal to 2 milliamps. And we have 3K in this path, 2K in this, so we have 2K over 2K plus 3K, which says that I1 triple prime is 0.8 milliamps. So then V0 triple prime is 0.8 milliamps times 1 kiloohm, which is 0.8 volts. So now, if we look at our source, look at our circuit with all three sources active, we'd have V0 is equal to V0 prime plus V0 double prime plus V0 triple prime. So here's one contribution from one source, another one. This gives V0 equal 5.6 volts when all three sources are active.